We are getting closer to the time for an exam. So again, I had sent you an email. You were supposed to send me input as to do you want the exam. It's going to be a take-home during family weekend, not during family weekend. You will have plenty of time to do it. I don't require everyone to do the take-home at the same time. So think about when you want it, and I will send out an email reminder about that today. Okay, how many of you remember Taylor series? Okay, so, okay, it's a start. So this is one of the big differences here between what used to be 105 and 106. Is, 106 assumes you know a Taylor series. And sadly, Taylor series is something that often gets somewhat missed in people's, travelings through the math department. So what I want to do is I want to review Taylor series and then talk to you about why Taylor series is so important for probability. And we've already seen Taylor series one time in this course. Where have we seen Taylor series? Bless you. So where do we use Taylor series? Which one? The birthday problem. As a way of approximating a very complicated function and getting a really nice answer that's extremely accurate. And if we had done a more involved Taylor series, if we had taken two terms, it would have been even better. Alright, so let me quickly review Taylor series. So the idea is, the more differentiable a function is, the better polynomial approximation we have. And so we'll let the nth Taylor series of f be the following. And so I'm going to expand about the point 0. You could, of course, expand about any point. It's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial plus dot 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 plus the nth derivative at 0 x to the n over n factorial. Could replace x with x minus a to expand at another point. So given any function, I'm replacing it with a finite polynomial. Or if I'm really lucky, I let n go to infinity and I get an infinite polynomial. Now, of course, one of the difficulties is how do you deal with something that's infinite? One of the whole points of this is to replace the function you're given with a series expansion that's easy to work with. So if I give you a Taylor series, especially if I give you an infinite one, you have a lot of questions to ask. So, given an infinite Taylor series, say, t infinity of f of x is the sum, and goes from 0 to infinity, the nth derivative at 0, x to the n over n factorial. What kind of questions might you ask about this sum? Yes?
Does it converge?
Does it converge? Good question. Before I ask anything else about it, it would be kind of nice to know it exists. What's the next question to ask?
Does it equal the function?
Does it equal f? So you get for free one point where the Taylor series will converge and it will equal the function. Which point is that? 0. Right? Because if you put in x equals 0, everything vanishes but the very first, or the 0th coefficient, f of 0. So it's really not that impressive to say we have a Taylor series that converges at 0. The question is, does it converge anywhere else? And unfortunately, that may be the only place it converges. I believe I've given you this example before. This is one of the worst functions in analysis. e to the negative 1 over x squared if x does not equal 0, 0 if x equals 0. Have we talked about this function? No. Okay. If anybody gives you a list of top 10 functions of mathematics, depending on your point of view, this is either on the list of the best functions or the worst functions. This basically shows you how badly things can go. Okay? This function is really nice, except at what point? 0. So the question is, what does this function look like near 0? Well, if you try to plot it, it's going to look approximately something like this. It has extreme decay near 0. Right? We have e to the negative 1 over x squared. If x is small, like 1 over a million, this is e to the negative million squared. Okay, this function really crunches down. Let's calculate its derivatives. How would I calculate the derivative of this function if x does not equal 0? So how would you calculate the derivative? Chain rule. So if x does not equal 0, chain rule. Derivative. X does not equal 0, chain rule. What if x equals 0? We have a split in the definition of the function. We have to go back to the definition of the derivative. F prime of 0 will be the limit as h goes to 0, e to the negative 1 over h squared minus 0 over h. Okay? This is the same as the limit as w goes to infinity of e to the negative w squared divided by 1 over w, if I just let w be 1 over h. The reason I'm doing this is I'm trying to make the analysis a little bit easier to follow. And rather than having h go to 0 with a 1 over h, I'm now going to have w going to infinity. So I can rewrite this as the limit as w goes to infinity, bring the w upstairs. So I have w over e to the w squared, with w going to infinity. How could I calculate that limit? So I want to know what happens as w goes to infinity. What could I do? I could do L'Hopital. This is actually a case where L'Hopital is fine. So it's actually a verb, you L'Hopital it. And after L'Hopitaling, okay, these are legitimate words. I mean, you won't find them in the OAD, it's limited, but. So you get a 2w e to the w squared, and that's just 0. So L'Hopital very quickly tells us that it's going to go to 0. We actually don't need to use L'Hopital. Another thing we could do is we could say, well look, e to the w squared is 1 plus w squared plus dot 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 dot. So this expression here is less than equal to w over w squared. And that goes to 0. So we actually don't need to do L'Hopital. Okay? So we've shown that the first derivative is 0. What do you think the second derivative is? 0. So as a nice extra credit problem, prove every derivative of this function at 0 is 0. Right? What does that mean? It means the Taylor series for my function, I can even do the infinite Taylor series, is identically 0. What this means is Taylor series are not unique. So as a nice example, I'm thinking of a function, okay? And the function has Taylor series is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus... What function am I thinking of? Nope. I'm thinking of sine of x plus 1701 over 24601 f of x, where f of x is the function from above.
Say sine x plus c.
Not plus c. Plus c would be wrong, because plus c would shift the zeroth Taylor coefficient. So it could only be plus c if c is 0. I can add any multiple of this function. And I can also find other bad functions. I can replace 1 over x squared with 1 over x to the 4th, and make it crunch down to 0 even faster. Taylor series are not unique. Okay? This is a horrible fact. So, after teaching this class, fortunately for me, I get to teach complex analysis. And in complex analysis, we don't allow functions like this in. In complex analysis, if a function is differentiable once, it's infinitely differentiable, and it equals its own Taylor series expansion. Complex analysis is far more elitist, exclusive, whatever word you want to use. We don't let things like this in. And it greatly changes the subject. So the question is, why am I talking to you so much about Taylor series? What does this have to do with probability? Well, one of the main things we're going to be doing today and over the next few days, is talking about moments and expected values. So moments and expected values. So I'll give you the definition, and then I'll talk and connect this to what we were doing a moment ago with Taylor series. So let's let x be a random variable with density f sub x. Right? Let's g be a nice function. Then the expected value, and we write expected value like this, square brackets g of x, means the integral from minus infinity to infinity of g of x, f of x dx, if it's continuous, and it means the sum over n of g of xn, and then the probability of xn if discrete. So if you think about it, what this is basically saying is I have some function g, and I look at all the possible values that it can take on, and I weight it by the probability that x takes on that value. You've all seen expected values, right? Where is a place where you've seen expected values? I'm sorry? Stats. I'm thinking of a grade conscious place where you've probably seen expected values. GPA, grade on an exam, what's the average score? I have all the students in the class, I give each student an equal weight, and then I can calculate how many points you got on your exam, I can add it up, and get the average value. These, you should think of these as generalizing average values. Now, in this class, I'm weighting everybody equally. There are some schools where not all students are weighted equally. Seniors are worth 4 times what a freshman is. Right? No, some schools say, your GPA senior year counts as 4, GPA junior year 3, sophomore year 2, freshman year 1. Yes, there's some schools like that.
Which schools? Can you give an example?
I think some of the military academies might do this. It's an interesting thing because, again, a lot of people are still learning and adjusting to college. You don't want a bad grade or experience in the very beginning to really throw you.
Yeah.
And so you can recover once you've learned and mastered how to adjust to college. So these are expected values. We're going to see many uses of them throughout. Okay? What do you think would be a really easy choice of g? G of x equals? So good. So one choice, that's the second easiest, is g of x equals x. There's one easy one which I will allow you to take. G of x equals 1. There's one easier choice in that I will not let you take. Yeah, g of x equals 0. I'm not really going to talk about g of x equals 0. So if I take g of x equals 1, what's the expected value of 1? 1. I have a probability density, right? It integrates to 1 or it sums to 1. So if g of x equals 1, no matter what the density is, it's 1. I'm basically asking, did something happen? And the answer is yes. Now I want to know, what's the average value? So if g of x equals x, this is giving us the expected value of x. And this is called the mean, and we often write it as mu sub x. Some people don't put the x down there and they just write mu when the random variable is understood. I prefer putting the x there to just remind myself, as always, this is coming from the random variable x. And so to calculate this, we would just need to integrate x times f of x, or sum xn times f of xn. Now you can see why calculus is a prerequisite for this class. Right? We need to be able to compute these things. So you might have some random variable that you care about, and you might be very concerned with the average value. If I tell you the average value, do you have a complete understanding of what's going on? No. What if I tell you the average value on the next exam is 80 out of 100? How do you feel? Do you have an understanding of what's going on in this? Well, that's different. Do you have an understanding of what's going on in terms of the grade distribution? Why not?
Because we don't
you don't know how much that's spread out. And so if I can only tell you one number about how the class is doing, and if you want to get a sense of how you're doing, okay, obviously you'd love to know, well, what's my grade? That's the best way for me to figure out what I'm doing. For Taylor series, if I wanted what the function is doing at a half, I'm not giving you the value of the function at a half. I only have information at the point 0. And the idea with Taylor series is to take knowledge at 0 and pass that on to elsewhere. And so if you try to think about what a Taylor series is doing, it's trying to get you better and better approximations locally, given local data. Yes?
But isn't it Maclaurin series that only focuses at 0? Can Taylor series be at any point?
Right, but a Taylor series can be a Maclaurin series as well.
Okay, yeah.
And so this is rectangle squarish.
Okay.
So let's say I tell you that at time 0, we are 5 miles from home. Okay? Where do you think you are 1 hour later? I'm sorry? What's your best guess?
Home.
5 miles.
5 miles from home. I haven't told you. Are we heading towards home? Are we heading away from home? Is the car stalled? Are we at the football game that we're watching? Right? I've given you no additional information. Your best guess is that for all eternity, you are 5 miles from home. So this is the 0th order Taylor series expansion. It's identically 5. If you could have one more piece of information, what would you love to have? Your instantaneous speed. So now, I'll say, at time 0, the speed is a whopping 2 miles per hour. Okay? I'm sorry?
Can we have velocity instead of speed so we know what direction we're going?
Ah, good. Thank you. Towards home. So the review dinner will be tonight around 5:30. Kayla and I have decided to walk there from the Children's Center. So hopefully we'll get there around 5:30. We may be just a little bit later. She says she wants to jog. I'm not quite sure exactly what jogging means for her. But where do you think you would be 1 hour later? What's your best guess?
3 miles.
3 miles. And so we would guess maybe T0f of x is 5 minus 2 times x.
T1.
T1, I think. And you could continue, and then the next thing you'd want to know is your acceleration. And the more information you know, the better approximation you can get. And the reason we have Tnf of x equals the sum, k goes from 0 to n of the kth derivative at 0, x to the k over k factorial, is by putting the k factorial down below. When we take derivatives, the powers of x come down, and they'll cancel the k factorial. So this will set it up so that the first n derivatives will also agree with the first n derivatives of the original function. That's why we put these k factorials here. Without those k factorials, it's not a good fit. So the idea is, the more information I know about my behavior at 0, the better I can approximate my function. It turns out moments are the same for probability distributions. It's very similar to Taylor series. The more moments you know, the better you can do at approximating your probability distribution. And so we need just a little bit more notation now, because so far we've only talked about one moment, the mean. So the kth moment would be the expected value of x to the k. I'm only going to write things with integrals, because I'm biased. We'll be integrating from minus infinity to infinity, x to the k, fx of x dx. And you often write that as the kth moment, and we'll put a prime there. The reason we put a prime here is the kth moment is not always the best thing to look at. How many people have taken a physics class here? Okay. If I have a piece of chalk, and this is a good piece, so I don't want to drop it, I'll take a crappy piece. I'm sorry? No, not staples. Oh, now great, now that's on the web, thank you. Alright, so if I drop the piece of chalk, how do I figure out what's happening to it?
Well, you need to know the acceleration.
So I know the acceleration of gravity. How do I figure out what happened to it? What equations do I use from physics?
The equation for motion.
Okay. So I've got F equals ma, and how do I figure out what's happening to this? I've got potential energy, what else do I have? Kinetic. So the potential is becoming kinetic. For potential, all that really matters is change in potential energy. I start off here at a value, and I look at how much I have over here. I can add a constant to the potential energy. All that matters is changes in potential. This is a very important thing when we're looking at probability distributions. If I pick up and slide the whole probability distribution down, it's going to just trivially change a lot of these things. And so what we often want to do is we want to normalize our probability distributions so we can compare apples and apples. And so if I measure my height in meters and if I measure my height in feet, will I get different values? Yes. Right? 1 meter is not 1 foot. Okay? But is my height actually different? No. I can adjust my scales to choose a convenient scale. Does anybody know the speed of light? Yes?
3.0 times 8 in a vacuum.
Approximately. Approximately. But a better estimate or a better value for the speed of light is 1. So these are called the rationalized MKS units, where the physicists have basically cleaned up the equations and they've made the speed of light equal to 1, they've made the gravitational constant equal to 1.
It's beautiful.
It's beautiful, but the problem is when I look at it now, I can no longer quickly see the physics behind the equations. I can see the mathematics, but I can't just quickly look and see where the different terms are coming from. But you can definitely renormalize things. And so for a lot of things, we can renormalize. And so one of the things we can adjust is we can adjust where's the mean. We can slide the distribution down. The next thing we can do is we can adjust the scale. I can't really add 5 inches to my height. That's not something I can really do that easily. But I can adjust the units I use to measure myself. Okay? And so I can adjust, in some sense, fluctuations about the mean in terms of the scale. So the k-centered moment is the expected value of x minus mu of x to the k. And this is just the integral from minus infinity to infinity of x minus mu of x to the k fx of x dx. Okay? The second centered moment has a beautiful name. We call it the variance of x, and we'll often write it as sigma x squared. If you've never seen the variance before, the notation should be a little strange. Why am I defining a quantity with a square? What this is telling you is the variance is not the fundamental quantity. Can anybody share their height? Roughly. Yes.
5'8".
You're approximately 5'8". 5'8" what? 5'8" Lego bricks?
Yeah.
Okay. Alright. So you're approximately 5, or was it
The
feet?
jumbo Lego.
Jumbo, okay, approximately 5.8 feet. What do you think, it's probably around average for, people. What do you think the fluctuations are about that? How much do you think people differ by? Think people differ by 2 feet? Maybe 2 or 3 inches around that?
You mean total or like
If you had to say ballpark, I think most people are around 5'8" plus or minus
5.
plus minus 5 inches. That's fine. Okay? I prefer something around 5 inches rather than something around 2 feet. I don't think fluctuations are around 2 feet. If x has units of meters, what will the units of variance be? Meters squared. So when you talk about, the average person is about 5'8" feet plus or minus 25 feet squared, plus or minus 25 inches squared. Inches squared is an area, right? If I'm talking about variations in height, I'm not going to talk about variations in height in terms of areas. So the standard deviation is sigma of x is the square root of sigma of x squared. this is the more natural unit to use. You want to measure how much you're fluctuating about the mean in terms of the units of the problem of interest. F of x is a probability. Okay? This is going to be a unitless quantity. And so when I look at x, I'm going to basically be getting something of size meters. Variance will be something of size meters squared. The idea, or the hope, is that if you know the moments, you know the density. So think back to when you were playing a game like 20 questions. You ask enough questions and eventually you get enough information that it uniquely specifies what the person is thinking of. I'm thinking of a probability distribution. You can ask for the mean, for the second moment, for the third moment, for the fourth moment. And if I give you all the moments, will you know the probability distribution? Given that I'm pausing, if you know all the moments, will you know the probability distribution?
No.
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 No. Bad functions can exist, right? We saw this with Taylor series. That I can give you a Taylor series where I know all the derivatives, I know all the coefficients of the Taylor series, but it does not uniquely specify the Taylor series. It does not uniquely specify the function. The same is the case here. Just because I know all the moments does not mean I know the probability distribution uniquely. Hope he knows. Okay? And the reason it fails is because, this is a math class, I'm allowed to say, bad functions exist. I can call it a bad function, okay? These functions do not have good properties. We need more information than knowing that all the moments exist. And so a really important question is, how much information do we need to know to uniquely conclude a probability distribution? It turns out, if we know the moments, not just the moments where k is an integer, but if we know the moments for a sequence of k that accumulate. So if you've taken, how many of you have taken real analysis? Okay, so if you have a sequence of k's that are not necessarily integers that converge to a number greater than 1, and we know the moments on that sequence, that will be enough. And so later I'll give you examples of probability densities that have identical moments but are different. And the problem is it's the discreteness of the moments we know, is we're only considering integral moments. If we allowed ourselves to study non-integral moments, then we would be okay. Need a sequence of moments, well, a sequence of k that accumulate. And so towards the end of the semester, we have a chance to talk about special topics. And one of the things we can talk about is the needed black box results from complex analysis to prove the central limit theorem. And so the first time I taught the course, I did it. The second time I taught the course, I did not do it. 2 data points is not enough for me to determine what the pattern is. It's a question of, do you want to see us opening up complex analysis a bit, getting a sense of what is complex analysis like, how do we prove this rigorously? Right now, when we get to the central limit theorem, I will teach it a la Moses coming down from Mount Sinai. He's going to bring us the extra set of 5 laws that were unfortunately lost, which include 2 beautiful theorems from complex analysis. Okay? And then if there's interest and time at the end of the semester, I'll talk about what do we actually need to make those work. Okay. Any questions so far on here on the moments? There are names for the third moment and the fourth moment. These are the skewness and the kurtosis. And they start talking a little bit about what the distribution is like. For the most part, when you take an exam here, professors might tell you the mean and they might tell you the standard deviation. I've only seen one class where the professor actually gave the first 4 moments of the distribution. I was visiting a friend at Harvard, and I guess the students there really are competitive and want to know exactly how they stand in the class. The professor listed for the intro physics course the first 4 moments of the distribution. Okay. A lot of these were pre-med students, so I'm not entirely surprised. The moments start telling you the shape. Now, an excellent problem for you to do is if I give you any probability distribution that's nice, you can adjust it to have mean 0 and variance 1. And in some sense what that means is you can compare apples and apples. And this is very similar to why when we talked about random variables, we want random variables to be real valued. We want to be able to add random variables to each other. We can't add a head and a tail. If my probability distribution is nice, I can always adjust the mean and make the mean 0. And then I can always rescale, go from meters to feet, to make the standard deviation 1. Now, of course, that assumes the mean and the variance exist. So let's do some problems. So let's look at the uniform distribution. So fx of x will be 1 if 0 is less than or equal to x is less than or equal to 1, 0 otherwise. What do you think the mean or the average value of this is? 1/2, right? This is symmetric up the wazoo, right? 0, 1, right? The mean should just be 1/2. What about the variance or the standard deviation? How big do you think the standard deviation should be? Or at least give me an estimate for the standard deviation. Could the standard deviation be as large as 2? No, I mean everything is defined between 0 and 1. What do you think an upper bound should be for the standard deviation? Probably 1/2. 1 would also work. 1/2 is, I think, a little bit better. I'd be shocked if the standard deviation was larger than 1/2, because that's basically enough to cover all fluctuations. Right? Nothing is more than 1/2 unit from the mean. So again, before you even start the problem, can you get a sense of what the answer is? So the kth moment is the interval from 0 to 1 of x to the k, well, technically minus infinity to infinity. Okay, now that we have this, remember the density is only non-zero if we are between 0 and 1. So this integral now becomes the same as integrating from 0 to 1 of x to the k dx. So we get x to the k plus 1 over k plus 1. That's 0 and 1, so we get 1 over k plus 1. So the mean is going to just be 1/2. How would I calculate the variance? What integral would I have to look at? So if I want to do the variance of x, what would I have to integrate? Yes?
Integral from negative infinity to infinity.
Yep.
X minus mu.
Which in this case is
1/2 squared.
Perfect.
Fx of x dx.
Yes. And so we would just actually have to evaluate this integral. And so here we'll be integrating from 0 to 1, x minus 1/2 squared dx. I think it's x minus 1/2 cubed over 3. Is that right? And now when I plug in, I get 1 minus 1/2, which is 1/2 cubed, which is 1/8, right, over 3 is 1/24. Minus, and I'll have negative 1/2 cubed is negative 1/8 over 3. Minus 1 over 24 is 1/12. Okay? So that's what the variance should be. And then the standard deviation would be the square root of that. And the square root of that would be 1 over 2 root 3. It's less than 1/2. So note, sigma x is the square root of 112, which is 1 over 2 root 3, less than 1/2. As predicted. Yes?
Where did the f of x go in between that process?
Well, f of x is identically 1 between 0 and 1, and 0 everywhere else.
Okay.
So it just becomes integrating from 0 to 1.
Okay.
Okay. So we've been able to calculate the expected value, we've been able to calculate the standard deviation. It turns out, there's a more convenient formula to calculate the standard deviation than doing this integral. So there's a shortcut approach. And so what I want to do now is I want to show you the shortcut approach. So assuming all below exist, the variance of x is the expected value of x squared minus the expected value of x squared. So what this formula tells us is order matters. If I have the square inside or outside, I'm going to get a different answer. Well, this makes sense. For instance, if x takes on negative values, the expected value of x could cancel out and be 0. And yet I would not expect the expected value of x squared to be 0, because I'm now forcing myself to have something non-negative. So the proof is the variance of x is the integral from minus infinity to infinity of x minus mu of x squared fx of x dx. And now the proof is basically just algebra following your nose. Expand the square. And I have the integral from minus infinity to infinity of x squared minus 2 mu x times x plus mu x squared fx of x dx. Okay, well now looking at this, the integral of a sum is sum of the integrals as long as everything is finite. So I now get the integral from minus infinity to infinity of x squared fx of x dx. Now, mu of x is a constant, so I can just pull that out. So minus 2 mu of x, integral from minus infinity to infinity of x fx of x dx, plus, and I can pull out the mu of x squared, the integral from minus infinity to infinity of 1 times fx of x dx. Okay. What's this integral here? What's the name for this integral? E of x squared. Now, minus 2, what's this integral? Mu of x, minus 2 mu of x times mu of x, plus mu of x squared, and then this was the easiest integral I could give you. Right? Integrating a probability density function is just 1. I have a minus 2 mu of x squared, I have a plus mu of x squared, it's a minus mu of x squared. And so I get the expected value of x squared minus mu of x squared, or the expected value of x squared minus the expected value of x squared. So this is a more convenient formula for calculating variances in many situations. If it's easy to calculate the uncentered moment, if I can calculate the second moment very easily, I can then use this to pass to the variance. And so over here, for this problem, I calculated for all k very easily as 1 over k plus 1. So for the uniform, the second moment would be 1/3, right? And then I subtract off the square of the mean. So what's 1/3 minus 1/4? I get 4/12 minus 3/12 is 1/12, right? Which agrees with what we had before. Okay, so it's always nice if you can check a formula to check the formula. Okay? So we now know how to calculate means, we know how to calculate variances, we can calculate all these moments. We will see, in maybe a week or two, lots of applications of these. But there's a natural question to have right now, and the question is whether or not these moments always exist. And so, this is one of my favorite examples. Cauchy distribution. So its density function is 1 over pi times 1 plus x squared. Now, I'm kind of begging the question, I'm kind of leading you, I'm calling it the Cauchy distribution. Do you think this is a probability distribution?
Yes.
Yes. What do you think it integrates to?
Pi.
1, right? If it's a probability distribution, it has to integrate to 1. If I didn't have the pi down below, it would integrate to pi. So the question is, how do you prove that this integrates to 1? One possibility is to go to the online videos I have for complex analysis. We actually did this integral using contour integration. You can do this elementarily without complex analysis if you remember an important fact. Yes?
Is the integral of 1 over 1 plus x squared tangent?
Almost.
Arctangent.
Arctangent. Alright, so you each have to email me a half point. Right? It's arctangent. So the derivative of arctangent is 1 over 1 plus x squared. And so if I try to integrate this from minus infinity to infinity, I'm actually integrating, the derivative of arctangent. What's the integral of the derivative of arctangent? Oh, that's not so bad. That's arctangent of infinity minus arctangent of minus infinity. What's arctangent of infinity? So tangent is sine over cosine. So I need an angle whose tangent is
Pi halves.
pi halves. Minus negative pi halves is pi. So the question is, how do I prove that the derivative of arctangent is this? If you have f of g of x equals x, then the chain rule tells you f prime of g of x times g prime of x is 1. Therefore, g prime of x is 1 over f prime of g of x. This is how we actually get the derivative of the natural log. By knowing the derivative of the exponential function is the exponential function, you look at the exponential of the natural log. So in our case, what is the tangent of the arctangent of x? What does that equal? X. What's the tangent of the angle whose tangent is x? If you read it out loud, right, I'm asking you, please calculate the tangent of the angle whose tangent is x. Right? It's just x. So we get arctangent prime of x is 1 over tangent prime evaluated at arctangent of x. Alright, so tangent is sine over cosine. You can use the quotient rule. You get tangent prime of u is 1 over cosine squared of u. The only thing that's tricky is we need to evaluate cosine squared of u at the arctangent of x. So to figure out what that is, you draw a triangle. I want an angle here whose tangent is x. Can somebody give me the lengths of 2 of the sides? Give me a triangle which will have a tangent of x. Yes?
Sine x and cosine x. Sorry.
No, that would give me
Yeah.
tangent of x. I want an angle whose tangent is x, not tangent x. X and 1. x1 square root of 1 plus x squared. The tangent of this is now x over 1. So the cosine of theta is going to be 1 over the square root of 1 plus x squared. And so the cosine squared of this will be 1 over 1 plus x squared. So arctangent prime at the angle whose tangent is x is 1 over 1 plus x squared. And that finishes the calculation. So this is a proof that the derivative of arctangent is 1 over 1 plus x squared. What's nice is this means we actually have a nice closed form expression for the cumulative distribution function. You know, this happens to be a distribution we can integrate. So now, the question becomes, what are the moments of this distribution? Can we calculate the mean? Can we calculate the variance? So we should have just enough time to make it through. So the mean, what integral do I have to calculate for the mean? So I want the mean of the Cauchy. So what should I be integrating? Integral from minus infinity to infinity, x times 1 over pi 1 plus x squared dx. What does that integral equal? There are two right answers for what this integral equals, and they're different. Can somebody tell me what this integral equals? Yes?
Well, you can... No, never mind.
Okay.
Or it could equal infinity.
Could equal infinity. What else could it equal? 0. I'm integrating an odd function about a symmetric region. It's natural to say it's 0. It's also natural to say it's infinity. In fact, you can have this equal whatever you want. The problem is if I put in absolute values, the integral diverges. Diverges with absolute values. For an integral to make sense, we need the limit as a and b go to infinity in any way they want. The integral from minus a to b of x 1 over pi 1 plus x squared dx to be independent of how a and b go to infinity. So if we let b equal a, we have the integral from minus a to a of blah, we get 0. If we let b equal twice a, we get the integral from minus a to 2a of blah. That's the same as the integral from a to 2a of x times 1 over pi 1 plus x squared dx. Because the integral from minus a to a cancels out. Now if you look at this, approximately if a is big, what does x over 1 plus x squared look like? It looks approximately like what?
1 over x.
Oh, right. So this integral is approximately 1 over pi, the integral from a to 2a of 1 over x dx. That's the natural log of x over pi evaluated at a and 2a. And after you do some algebra, you get the natural log of 2 over pi. And so unfortunately, this does not have a mean. Okay, it's sad. Okay? It clearly does not have a second moment. If I replaced x with x squared, my integrand would look like x squared over 1 plus x squared. Oh, that looks like 1 for large values of x. Okay? So you can argue whether or not it has mean 0. I'm willing to accept that it has mean 0. That I can deal with. But I will not accept that this has a second moment. So the problem is, not every probability distribution will have moments. So our dream of looking at nice probability distributions whose moments will then determine what goes on, well, if I don't even have moments to play with, there's no chance to use these tools from complex analysis. And so it's going to become an interesting fact as to how do we handle distributions like this. There's a generalization of moment. Can everybody picture in their mind what the mean is? The average value? Can you picture what the variance or the standard deviation is? We need to take imaginary moments. Okay? If we take imaginary moments, everything turns out to be okay. And so this is where a lot of complex analysis and advanced machinery comes in. The imaginary moments always exist. It's called technically, I say the Fourier transform because I was trained as a number theorist. The people in probability theory, they say characteristic function, tomato, tomato. The main thing is, if you use imaginary moments, the integrals always exist. The imaginary numbers always have absolute value 1, and the integral of my function is finite. In fact, the integral of my density has to be 1. As we've seen a lot of nice techniques today. We've begun to see the moments. We're building up now some of the machinery we need to study probability density functions. Okay, the review dinner will be around 5:30. Kayla said she will jog. We will see how